Hey folks, it's Dr. Gilchrist, and we are starting with a brand new chapter. We are moving our way to a brand new sense. So we are done with vision, and now we're going to talk about hearing. Now, typically, what we're going to find is that for human beings, for most of us, vision is definitely our most used sense. And so, one of the things that we often find is a phenomenon known as visual capture. So, this is basically the idea that we use vision so much that it has a tendency to take priority over our other senses. Now, despite that, we're actually pretty good with our hearing as well. So we're going to click on these different speakers in this Companion Site's web activity, and let's go ahead and see if we can identify these different creatures. Okay. Yep, odds are pretty good. You identified that as some type of frog. Let's go ahead and try this one. So that's the sound of running water or rain. Let's try this one. That definitely sounds like an airplane. So I'd encourage you to go to the Companion Site and try to see if you can identify all of these different types of sounds. Now notice that for all of these, you were able to identify the object without even having to see it. Okay, so we're going to go ahead and move back here. We will do some other types of web activities, but I want to go ahead and get started with talking about the basics of hearing. So this is a pretty long lecture. These do have a tendency to kind of run into each other, but as much as possible, I will try to whip through this as quickly as I can, and I want to make sure that if there's anything you don't understand, feel free to ask. So we're going to talk about the physical properties of sounds. Then we're going to talk about the properties of the auditory system, both the auditory system that's present in the ear and then moving up to the brain. And then finally, we will talk about how the auditory system operates. We will also talk about ways that the auditory system can potentially be damaged, including things like hearing loss. So you're going to hear me basically sound like an old and tell you, hey, be careful when you listen to headphones. But largely, we're going to focus on these major things. So we're going to start by talking about the physics of sound. So again, remember that this is a class in sensation and perception. So when we're talking about the process of sensation, we are actually taking physical stimulus energy from the environment, and we're going to try to convert that into a signal that our brain can actually use, process, and later interpret into something meaningful. So what this means is that for things like sound, just as light has physical properties, sound also has physical properties. So sound begins with the formation of pressure waves. So sound is transmitted through a medium through pressure waves. Sound waves are created through object vibration. And depending on the medium, this will set molecules of that medium, be it air or water or a solid, into motion. So one of the things that we'll find is that if you want to be able to hear a sound, molecular collisions are really, really critical. Part of the reason that sound transmission is often very difficult to do in the vacuum of space is that there's not really a lot of opportunity for those molecular collisions to occur. There's not really any air there. And because of that, sound can't be transmitted. So when these molecules of air, water, or a solid are set into motion, this basically creates different types of pressure changes that can be detected by the auditory system. And this will include alternating areas of compression where the molecules are very tightly packed together, and expansion, which is also known as rarefication. So here's kind of an example of what this looks like. So in this particular case, we have a speaker transmitting a sound. We have areas that are rarefied. We have areas that are compressed. And these different vibrations in air molecules will eventually make its way towards the ear and the ear canal. So the sound wave, generally speaking, the pattern of fluctuation is going to stay the same over a distance. So what this means is that this little sinusoidal pattern always stays the same. So this sinusoidal wave helps you understand the frequency of the sound. Now what you'll kind of notice though is that the intensity, the amplitude of each of these waves decreases with distance. So what this tells us is that over distance, the frequency or the pitch of a sound will stay the same, but the intensity or the loudness of that sound will decrease with increasing distance. Now, what is the speed of sound? Well, it depends on the medium that sound is surrounded in. If it's in air, that's about 340 meters per second. In water, it's actually even faster. It's about 1,500 meters per second. Now, some of you might find this kind of surprising because if you've ever played a game of Marco Polo, if you're underwater and somebody is outside of the pool yelling at you, you won't be able to hear it. But part of the reason that this happens is because that sound has to be transmitted from air to fluid. If you're already in water, the molecules are more tightly packed together. And what this means is that the sound wave has more opportunity to basically cause all of these different molecular collisions. So that's part of the reason why the speed of sound is much higher in water. So we're going to have more collisions, but because water is a heavier medium, you need to actually have more energy to start that sound wave. And if you're going from air into water, a good chunk of that energy is going to be lost. So let's talk a little bit about some of the different properties of sound waves. So first of all, we have amplitude or intensity. So this is the magnitude of the displacement of the sound pressure wave. So basically, how high is that sound pressure wave in terms of its peak? This is what we perceive as loudness. So the louder the sound, the greater the intensity, and the larger the amplitude. When we talk about the frequency of a sound, we're talking about the number of times per second, or hertz, that a pattern of this fluctuation of pressure repeats. And this is what we perceive as pitch. So higher pitched sounds tend to have a higher frequency. So here's what that kind of looks like. So here we have our amplitude here. That is measured as sound intensity. So loud sounds will have a large amplitude. Soft sounds will have a lower amplitude. Frequency is our perception of pitch. Low frequencies, you can see that there are very few fluctuations from high to low to high. With a high frequency, we're going to see a lot more fluctuations. Now, we will talk about this a little bit briefly. Sounds can also be simple sounds, or they can be complex sounds. So they can be simple tones that sound like this one that I'm generating from my app. So that's a case where that's a pretty simple sound. It's a very simple sinusoidal wave. However, most of the sounds that we hear out in the environment aren't pure tones. They're made up of different combinations of frequencies, which we perceive as timbre. Timbre is what allows us to tell different musical instruments apart from each other, even though they're all playing the same note. And it's also what helps us distinguish our friends' voices from each other. They're all made up of different types of frequencies. So here's kind of another example. So here we strike a tuning fork. We get these different areas of compression and expansion. You can kind of see that this helps correspond to our waveform. So here we kind of have our low points. Here we have our peak. And you will notice that over time, the sound does become a little bit less intense. But here we have our wavelength, so our frequency. And here we have our amplitude. So generally, the greater movement, the greater amplitude, the larger the amplitude gets, the louder the sound. If we have greater frequency, the amplitude will stay the same compared to this original one, but you can actually see that the frequency doubles in rate. So how do we measure these properties? Frequency is typically measured in hertz. That is the number of cycles per second. That awful sound that I played for you was about 2,000 hertz. So 1 hertz is 1 cycle per second. Amplitude or intensity is usually going to be measured in what we call decibels. This is actually a ratio between 2 different sound pressure levels. So if we have a 10-to-1 sound pressure ratio, that is basically 20 decibels. If we have 100-to-1, that's 40. Human speech is usually between about 40 and 70 decibels, depending on how loudly or quietly you're talking. So let's take a look at our range of human hearing. So there is our frequency that we just heard for that tone. That's about 2,000 hertz there. Now, as with vision, we do have a limited range of frequencies and sound pressure levels that we can actually hear. But of what we can hear, as you can see, there's a pretty wide range. So here's our range for speech, both in terms of frequency and in terms of sound pressure levels. Frequency is on our x-axis, sound pressure levels are on our y. The audible range in terms of frequency basically is as low as about 20 hertz, but you have to have really loud sound pressure levels to be able to hear that. As we get into higher frequencies, they do not have to be as loud to be able to hear them. And finally, kind of at our upper point at 2,000 hertz, you can see there's kind of a cutoff there. We really can't hear anything higher than about 20,000 hertz or so. For our high risk threshold, that is a sound that is basically about 115 decibels. If we have about 135 to 140 decibels, that is actually going to produce pain. Speech tends to fall in this area, music tends to have a wider range, and our audible range in general is pretty good. Now, the ratio between the quietest sounds that we can hear and the loudest sounds that we can hear are about 1 to 1 million. Now, one thing that I do want to impress, because decibels are functioning kind of as a ratio of sound pressure levels, decibels are actually measured on a logarithm scale. So a decibel is about 20 logarithm of the pressure of sound against a reference pressure level. So what this means, because this is a logarithmic function, a very small change in decibels can actually mean large differences in loudness. If we have an increase in about 6 decibels, that is actually a doubling of sound pressure based on this logarithmic scale. Here are some pretty common everyday sound pressure levels. Leaves rustling is about 20. Being in a quiet library is a little less than 40. Being in a business office is a little less than 70. Being stuck in traffic and listening to a heavy truck is about 90. A jackhammer is right over 100. And a jet takeoff without any sort of auditory protection actually has a sound pressure level of about 135, very, very close to our threshold of pain. Now, let's briefly talk about those pure tones and those complex tones that I mentioned. Pure tones will basically create a sine wave, and the waveform corresponds to a sine function. As I mentioned, very few sounds in our environment actually correspond to pure tones. Most of the sounds that we encounter are complex tones with a mixture of different sine waves, which means that any time that we are engaged in listening to a complex sound, we are looking at those different frequency components that make up that tone, which means we're basically doing a Fourier analysis. So complex tones often involve a combination of frequencies, and you can actually think of these different waveforms in terms of a spectrum. So here, I can't get out. Oh, I couldn't get out there for a minute. I lost my cursor. Okay. So common sounds, as I mentioned, involve a combination of frequencies. You can think of these waveforms in terms of a spectrum. So here's our pure tone. If we map the spectrum against frequency, there's only going to be one spectrum here. If we have a higher frequency, it will look like this. If we combine both of those A and B waveforms to create this, you can see that those two different frequencies are additive, and they actually match up with each of their waveforms' individual spectrum. If we have something like a square wave, you can actually see all of the different component frequencies that make that up as well. So one of the things that's interesting is that a lot of complex tones or sounds, especially if you're talking about music or singing, actually have what are called harmonic spectra. So the energy is always occurring at multiples of a fundamental frequency. And a fundamental frequency is the lowest frequency component of a complex periodic sound. And this usually comes from a simple vibrating source. That could be things like guitar strings, clarinet reeds, singing a song utilizing the vibration of your vocal folds. And so that's what really actually separates music from noise. Music is very organized around these multiple harmonic spectra. Noise has different spectrums, but they're not organized in multiples. They're random, and that creates noise. So here's something kind of interesting. We're going to look at all of these different instruments here. So here's a pure tone at 262 hertz, corresponding to a C note. Here's a tenor saxophone, a trombone, and a piano. They're all playing the exact same note as this pure tone. But notice that depending on the instrument, we have more harmonic spectra that are actually involved. Now note, every single one of these instruments does have the same fundamental frequency that matches the pure tone of 262 hertz. But the remaining spectra are all multiples of that 262 hertz, and they're organized in different ways. So you'll notice, for example, that a tenor saxophone has an incredibly complex waveform. Look at all of these different spectra that are involved. So does a piano. A trombone, which is a wind instrument, a brass instrument, has considerably less. But because these all have different complexities, you can actually tell the difference between these different instruments despite the fact that they might be playing the same pitch and they have the same loudness. So timbre is conveyed by the different harmonics and the higher frequencies. So now let's kind of move on and talk about the auditory system. So how are sounds actually recognized and processed? So the auditory system is involved in this in a series of different stages. So we have different portions of the auditory system with different functions. So we have our outer ear, which basically is the fleshy portion of our ear that we can touch with our hands. It also includes our ear canal and our eardrum. And this is basically to funnel sound into the middle ear. The middle ear's function is to amplify sound before it reaches the inner ear. And then in the inner ear, that's when sound is basically translated into a signal that the brain will actually use. And depending on the type of animal, that animal, particularly mammals, they will evolve to detect very specific types of sounds. Very generally, the smaller the animal, the higher the frequency it can hear. I played some of these other different tones, much higher pitches than I could hear on my phone, and my cat actually turned to look at me. Compare that to dogs versus elephants. Dogs will generally be able to hear higher frequencies than elephants will. So let's start by talking about the outer ear, and you can actually see the outer ear is here. So sounds are going to be funneled in and collected by the pinna. So the pinna is the cartilaginous portion of your ear. It's kind of shaped in a funnel sort of way, and if you feel around your ear, you'll actually notice that there are these small little grooves that basically help direct sound, help you localize sound, and also help that funneling process. So the pinna is basically going to funnel in and collect all these sounds. Sounds are going to enter the ear canal. The ear canal basically extends about 25 millimeters into the head, and they actually do enhance frequencies between 2 kilohertz and 6 kilohertz. So that's 2,000 hertz through 6,000 hertz. And then finally, as the sound waves get filtered into the ear canal, they will basically cause the eardrum or the tympanic membrane to vibrate in response. And this is going to become really important for the middle ear. We're going to go ahead and stop here and take a quick break, and I will talk with you very soon.